we got IR spectrum here, and then you want to find out this spectrum is belong to any of these structures shown up here. So we're trying to recognize signal that we can use to solve it. What is a very distinctive in the structure here? I would first point out that yes, this sharp band about 330, 300, that's very easily recognizable, right? This is a sharper than normal OH. If it's an OH alcohol, it will be broad, right? I think this is too sharp and narrow. Along with that, we have a signal at 2100. 2100, with this reason, if you don't have a triple bond, you normally don't see anything. So having band there is pointing out that we have a triple bond. This is a 2100, kind of small, and then along with this, I think we have a triple bond carbon with a hydrogen on it, something like this, right? That is kind of a very characteristic to show that. I mean, if this is a molecule has to be that one, then we need to see the carbonyl, right? Carbonyl is something that you cannot miss. But I don't see any signal at 17. I mean, it's a conjugated ketone. The number is going to go down even below 710. But anyway, this is a region where it shows I got nothing. So whatever this molecule it is, it does not have a carbonyl. And we can say that. No carbonyl. And then we got triple bonds. And then triple bonded carbon have a hydrogen. So not this, not that, because all of these things have a carbonyl. This is the only one without the carbonyl, having a triple bond and a hydrogen there. So we can say that this spectrum belongs to this molecule. So this is kind of a things that what you're going to do. Yeah, basically this is what I described. Same thing. All right. The next one. Next one, we do have a strong signal down here. It's about 1720. So 1720, it sounds like a very typical carbonyl stretching signal, maybe coming from the ketone. It could be aldehyde. It could be carboxylic acid. To be a carboxylic acid, we should have a very big, broad OH signal there, which we don't see at all. So this cannot be the carboxylic acid. Then can this be aldehyde? Aldehyde normally have a signal 2700, 2800. So those two signals there, that's the one, that's the peaks bands pointing out that it could be aldehyde along with this carbonyl signal. So this and with that could point out that yes, this may be this aldehyde. I mean, there's only one aldehyde in the choices, but that could be the only aldehyde you see. And there are other things you could point out. I mean, just in case you have an aldehyde here, you've got another aldehyde, then, I mean, we can make the question that difficult. You have to still choose which aldehyde it could be. Then you've got to use other information. For instance, there's a 3000 line right here, right? 3000 line goes right there. Right? We got peaks coming above the 3000. What does that mean? Is the molecule is a double bond. So there's an unsaturated carbon signal there. And then the peaks 1600. Typically 1600 is a kind of very typical numbers for the benzene. So along with this unsaturated signal and that one, we could politically say that yeah, that benzene unsaturated carbon in there in the molecule. So this aldehyde, yes, this is an aldehyde there, must have some kind of double bonds. Probably benzene because of 1600 signal. There's one other thing I want to point out, which is this example. We do see a peak there. That small band going down about 3400, little over 3400. Looks like an amine, right? If it's an OH, it could be probably this big. If it's a carbon triple bonded carbon hydrogen, it could be very sharp. But this is kind of small. It's a single spike, so you may say that this might be the NH. It looks like it. But this is the one that you have to be careful. That is actually not, this is not an amine. This is caused by the carbonyl. The carbonyl makes that signal come out. The reason is like this. Whenever you pull up the guitar, right, if the strings oscillate, it goes up and down. But it doesn't make just one note. If you actually analyze the spectrum of the sound, you're going to see that the first harmonic shows up along with the second harmonic. So it's not just single notes coming out. You've got the first harmonic, second harmonic is coming out. Their intensity is going to be lower. But if you play a single note, this huge signal makes a little bit of an overtone showing up in the spectrum. So this does not belong to the mean. This belongs to the strong Corbinius first harmonic, second harmonic. So when you see the Corbinius, strong Corbinius there, and this is 1720. So if you double it up, it's a 3400. So that's kind of belongs to 3400. Maybe 3450. I don't know if that's the number, but this is actually caused by strong Corbinius signal. If you see this without the Corbinius, then you may have to suspect that maybe it could be a mean. But if you see that with the Corbinius, then this might be just overtone coming from the Corbinius stretching signal. So that's something you got to be careful. All right, the next one. We do have a strong signal going down there, right? That's the first thing you can recognize it. And then the number is that's 17, 20, 30, 20, 40, and 60. I would say 1760. The 1760 is definitely higher than 1720, typical Corbinius numbers. Only one thing makes the Corbinius stretching signal goes higher, and that is an aster. Right? So this signal points out that we have an aster. But we have this aster, we have that aster. So we have two different types of aster here. So we need to figure out which one it belongs to. I mean, there's other things that we can also point out there. First of all, we got 3000 lines, we got stretching signal only coming out a little above, right? So that means that we got unsaturation. But both of them has a benzene, so it does not really narrow down. It only points out that yes, we have an unsaturation in the molecule. That points out like this. And then the signal at 1600, that means that we have a benzene, but both of them has a benzene, so it doesn't help us. Oops. So what else should we use to figure it out? That is a question. So let me first point out, remember, you know what that thing is now, right? That small thing there, that's coming down close to the 3500. That is definitely the overtone of this. So now you see that it appears a lot with the Corbinius signal. So now you can simply ignore that. Now we're talking about aster as a choice of the molecule, but we got two different ones. So how do you figure out which one is an answer, which one is not? Can we still talk about? First of all, this Corbinius with an oxygen there. This is an aster bond, right? There's a Corbinius and an oxygen here. This is an aster. But what you should see is this Corbinius is conjugated to the double bond, benzene. The aster typically high number, like a 70, 60, for instance. But if it's a conjugate there, then it's going to come down like a 20, 30 down. So that should come down lower. So that is the kind of things we should look into. This is not conjugated aster. This is a conjugated aster. So numbers are as high as 1760 is pointing out that this aster is not conjugated at all. So this should be the choice, not that one. That makes the Corbinius go down because of the conjugation to benzene. Anyway, so that we're going to talk about a little bit later because we have a spectrum for that. This one here, the Corbinius, the strongest signal there, that's about 1700. That's a 1700. I mean, 1720 is a typical number. 1710, it went down a little bit. So you may think that this could be negative ketone, it could be aldehyde, or it could be conjugated ketone. You may think like that. Let's find out what it is there. I mean, first of all, You got 1700 right there. Oops. And then typical ketone number set to 10. This is a little down. If it is a ketone or aldehyde, first of all, there's no, there's a ketone here. And then we have a double bond here. So if a double bonded ketone makes it probably go down more than this, 1700 is kind of a little higher than the conjugate ketone. It will go down to 1680, 1670, or that region. I don't think that's below the conjugate ketone because these numbers are not low enough. And then what I'm trying to point out that this is not aldehyde because we don't have that 2800 stretching signal there. And then this is not an ester we just talked about in the previous slide because of that. This is supposed to be really high. It came down as a 1760, right? Remember that. So this frequency 1700 cannot be this one. It's just too low for that. And then this is a conjugated ketone. It's just normally like a 1680. This is a little too higher than that. So this is not this, not that, not this one. Definitely not that one because that doesn't have a carbonyl. So only thing left is this one. But this is an ester. Why an ester shows such a low wave number? Because if it's an ester, it should be high number, like a 17, 30, 40, 50, you know. So it should be higher than normal numbers. This carbonyl, this ester, shows 1700. So why is that? Is what I told you earlier. It's an ester, so I'm expecting like a 1730, for instance. But this is a conjugated double bonds right there. So it's a conjugated ester. So normal ester could show like a 1730, but because it's conjugated to the benzene, it goes down. So if you subtract that, it could just becomes like a 1700 range. So the structure influenced the position of the carbonyl. So that is some kind of other information that you need to look for when you need to narrow down the choices. So these are something that you should do to practice the questions of an IR, right?